We normally think of the universe in four states of matter: solid, liquid, gas, and plasma. But when we reach temperatures a hair away from absolute zero, the point at which atoms have zero internal kinetic energy, a fifth state of matter is created, the Bose-Einstein condensate. The Bose-Einstein condensate was predicted in 1925 by Satyendra Bose and Albert Einstein. However, it wasn't until 70 years later when the first Bose-Einstein condensate was produced by Carl Weinman and Eric Cornell. For their work, they received the 2001 Nobel Prize in Physics, along with Wolfgang Ketterle. Crucial to understanding the Bose-Einstein condensate is wave-particle duality, or the idea that every quantum entity can be described as both a particle and a wave. While this concept is well known in regards to light, people often forget that it applies to matter. The de Broglie relationship states that the wavelength of a particle is inversely related to the velocity, and because a lower temperature creates a lower velocity, the lower the temperature of a particle, the longer the wavelength. So let's take a gas and cool it down to a billionth of a degree away from absolute zero. As the temperatures drop, the wavelengths become longer and longer, forming quantum wave packets. Eventually, these packets become so long that they overlap, and once they overlap, each atom begins to oscillate at the same rate, and they become indistinguishable, forming a single matter defined with one wave function, the Bose-Einstein condensate. One way to think about this condensate is as if the atoms are bees. As an individual, each bee is able to fly around and function on its own, just like an atom would. However, when the bee returns to the hive, just as when the atoms are cooled to temperatures near absolute zero, the bee now acts with the hive mentality, just as the atom now acts with a single wave function. Through the Bose-Einstein condensate, we are able to learn so much about the natural quantum properties of atoms. Bose-Einstein condensates are extremely important for learning about quantum systems due to their peculiar lattice structures. And although the Bose-Einstein condensate is an extremely fragile state of matter, the control over the matter is extremely precise due to the low motion of atoms. Humanity always thinks that it has a tangible grasp of what is around us, but science continues to challenge those worldviews. No one expected a fifth state of matter, much less that we could reach it, but the Bose-Einstein condensate proved us wrong. And the fifth state of matter has shown that we've only grazed the surface of what the universe has to offer.